Hey, good morning. You guys made it. I don't like getting up when it's dark still. Yeah. My gosh. All right, let's see. All right. Teaching. Right. And I don't know if there's a. Oh, the screen's over there. I had it right home. Okay, good. I'm sorry to wake you guys up so early. My gosh. You know what they do here, I think, is if you have a class like later in the day, even in the afternoon, they always put your final exam at 7:45. Just throws you off. I don't remember what time the final is in this class, but we'll see. Okay. All right, let's get started. 8 o'clock. So yeah, it's great that you guys made it in a little bit earlier today, but we'll try to make this an excellent lecture. Hopefully you all got the announcement that homework is not due till midnight instead of right now, or instead of at 9:30, right? And the office hours today are moved to 4 o'clock, 4 to 5. All right. So come by there if you need help for your homework from 4 to 5, and then make sure you have your homework in by 11:59 p.m. as a matter of fact, on Canvas. All right, great. Okay, so we've been previously talking about all the properties of waves that travel in unbounded media. We looked at homogeneous media, linear isotropic, all those goodies. Then looked at anisotropic media. We found that there were two normal modes. They had their own indices of refraction in different directions, and therefore led to waves that travel at different velocities. And so the index of refraction that the wave sees depends on the polarization of the electric field, and by having two waves traveling at different velocities in the same direction, because they're polarized in different directions, leads to conversion of linear to circular or elliptical polarization in anisotropic media. We looked at briefly what periodic media, infinite unbounded periodic media, and what kind of waves we would see in there. And we derived the Floquet theorem. Okay, now we're looking at the presence of interfaces between two dissimilar media. So we have two infinite unbounded spaces. They're called semi-infinite because they exist in half space. So they go from some interface value, say z equal to 0 off to infinity. You have properties epsilon mu 2. And then you have region 1 from z equals to 0 to minus infinity, where it has medium properties epsilon 1 and mu 1. And in this medium, we have an incident plane wave. In this case, they're normally incident plane waves. We have one traveling at, so we have an incident plane wave traveling in this direction, incident upon the interface. And it's polarized in this direction, which we call the x direction for now. The way to set up these problems is we assume that there are two other waves in general. There is a transmitted wave into medium 2. And if that transmitted wave, say, becomes 0, then we will derive conditions that stipulate what the amplitude of E transmitted should be. But for now, we assume that there's in general a transmitted wave polarized in the same direction as the incident wave. And we have a reflected plane wave, which is also polarized in the same direction as the incident plane wave. So that's the key to setting up these problems. We have three waves. We have an incident, a transmitted, and a reflected. And the key is that they're all polarized in the same direction. And we'll see that this is a choice that we use to break to set a convention and break an ambiguity. Okay, because it's not guaranteed, right? We don't know at this point if this reflected electric field will be in the same direction as the incident, right? Or even the transmitted. But here we're going to say we'll solve the problem by assuming that they're all polarized in the same direction. And if there is a change in the direction of polarization, when we apply the boundary conditions, we will see that. All right. Once you know the electric field and the direction of propagation, you can use the right-hand rule to find the magnetic field direction. Here we have E cross with H gives us the direction of propagation. And in the reflected field, since we're going that way, it's E cross H gives us the direction of propagation, H going into the board. All right? And then the transmitted field is the same. Okay. So now all you have to do is write down the form of the electric field for all of these different cases. We have the incident field is X polarized, E naught, E to the minus J beta 1Z. So now what you're going to see is a subscript to the wave number indicating which medium that wave number is a part of, because beta is omega square root mu epsilon, right? So if the permittivity is different, then the wave number will change, all right? Okay, and you know how to find the magnetic field fast for plane waves. We use the right-hand rule to find the direction, and we divide by eta to get the amplitude. And it has the same propagation term, phase term. So in this case, we also have a different impedance in each medium because eta is equal to the square root of mu over epsilon. So if epsilon changes, or mu, then so does the wave impedance. All right? We could do the same thing for the reflected field. But now what we're going to do is we're going to say, we don't know exactly what the reflected field amplitude is, but we're going to write it as some kind of weighted weighted superposition, or maybe not superposition, but some constant multiplied by the incident field's amplitude. All right? We're going to write it in with respect to the incident field amplitude. So the incident field, we know. We're going to say that's E naught. But the reflected field amplitude, we don't know it yet, right? So we're going to just say that it's some constant. We're going to call it gamma B. Could be a complex constant. But we're going to say it's some multiple of E naught. All right? And it's now traveling in what direction? The minus Z direction, right? So it's going to have a plus here rather than the minus. Okay. Yeah, beta dot r always works. E to the minus j beta dot r. Then you have to find what the beta vector is. You got to resolve its components and do the dot product of that vector with the position vector r, right? No. So beta dotted with r, right? Well, beta is beta x, x hat plus beta y, y hat plus beta z, z hat. And r is x, x hat, y, y hat, z, z hat, right? Now, what is beta in this case? Beta is this vector here, isn't it? Sometimes called k or beta. And these are the incidents, right? So that vector is purely along the z-axis, right? So that means that beta is equal to beta z, z hat only. And when you do this dot product here, you're going to only pick up this term, right? Because the other two vectors are orthogonal. So this will be beta z, z hat. Now, once you find this beta z, z, oh, sorry, that was terrible. Hold on. It's beta z, z. All right? Now what you do is you say, once you calculate this quantity, to find the phase constant or the phase term, you say e to the minus j beta dot r. This will be e to the minus beta zz, which is what we have here. Beta 1, right? Okay, good. All right. So we write the reflected field amplitude in terms of the incident field amplitude, and then we use our rules to find the magnetic field. Divide by the wave impedance, use the right-hand rule to find the direction, right? So here, look, we know that the reflected field's x hat. We know that E crossed with H, whatever H direction is, has to give us the direction of propagation. In this case is minus Z, right? So E crossed with minus Y would give you minus Z, right? So this has to be minus Y hat. That gives you the direction. The amplitude, you take the amplitude of the reflected field, which we're writing it as gamma B into E naught, and you divide it by the wave impedance. This is medium 1. Now the transmitted field, it's the same as the incident field, but we're writing it in terms of the incident field as well. The amplitude is what we're going to call the transmission coefficient, multiplied by E naught, and then e to the minus j beta 2z, and then eta 2 here, right? All right, good. So one of the hardest parts of doing these problems is to write out all the field components. Once you write them all out, you just apply your boundary conditions, and then you're done. All right, so now we apply the boundary conditions at the dielectric interface. We know that the boundary condition for dielectric is tangential E and tangential H components are continuous. Therefore, what we could say here is E incident. So if we apply tangential E has to be continuous at this interface. At this interface, tangential E has to be continuous. That means that E incident plus E reflected has to equal to E transmitted, right? Because tangential E on the, so what does tangential E continuous mean? It means the electric field on the left side of the interface is exactly equal to the electric field on the right-hand side of the interface in terms of its tangential components. The total electric field on the left side is the incident field plus the reflected field. The total field on the right-hand side, well, there's only the transmitted field. So those have to be equal. So what do we have? E incident. So we set this equality. I'll do it really quick for you. E incident is E naught, e to the minus j beta 1z, and E reflected is gamma b E naught, e to the plus j beta 1z is equal to E transmitted T times E naught e to the minus j beta 2z. All right. So, okay. So what we do here is we cancel out all of these E naughts, right? And then, yes, exactly. At z equal to 0, so then all of these go away. And you get 1 plus gamma b equal to TB, right? You get this. Very good. So you guys have probably seen this before, hopefully. All right, good. So 1 plus gamma b equals, so the transmission coefficient is equal to 1 plus the reflection coefficient. That's what these are. This gamma is the reflection coefficient, and this capital T is the transmission coefficient. And the superscript b means at the boundary. Because you can also reference a reflection coefficient. If I know the reflection coefficient here, I can also write it over here, some distance away from the interface by, there will be a couple of exponential terms. We'll see that. Thin film infinitesimally close to a boundary, and then you illuminate it at an oblique angle? Yeah, we'll do that. We're going to do oblique case. So let's wait and see that. Okay, if you do the same thing for the reflected field, so, okay. You can solve for the reflected field. You'll end up with 2 equations, 2 unknowns. You can solve for the reflected field using the magnetic fields. And then you'll get this equation. Hopefully you've seen this, at least in transmission line theory, it must be familiar. Gamma b equal to a to 2 minus a to 1 over a to 2 plus a to 1. That's the ratio. The reflection coefficient is defined as the ratio of E reflected over E incident and or minus H reflected over H incident. So remember, if you're working with reflection coefficients, normally it's defined, at least in what I'm used to, is the ratio of the reflected field to the incident field amplitudes, right? But you can also define a reflection coefficient in terms of the magnetic field amplitude ratio, but it will involve a minus sign. All right, and you can readily derive these expressions as well, where we have the transmission coefficient is 2a to 2 over a to 2 plus a to 1. And it's also related to 1 plus gamma into TB, of course, and then you can relate it also to the magnetic field. Okay, good. So you probably have seen these, hopefully. So once we have the electric and magnetic fields in each of these regions, we have the incident electric and magnetic field, the reflected electric and magnetic field, and the transmitted reflected and magnetic field. We can calculate their power densities. And what we see is, so for the incident field, it's 1/2 E cross H conjugate. And what we end up with is magnitude E squared over 2a to 1 in the Z direction, right? The reflected field, if you do the same thing, you get minus gamma b squared E naught squared over 2a to 1. And what you'll see is the square of the reflection coefficient's magnitude determines how much power is reflected, right? Because the reflection coefficient is a ratio of field amplitudes. So if you take the magnitude and square it, then it's a quantity that relates power, right? Okay, the transmitted power density, 1 minus gamma squared times S average incident. I'm sure you've seen this before in terms of S parameters. All right, and if you ratio the power densities, you get gamma b squared, reflected to the incident power density. If you ratio the transmitted to the incident power density, you get 1 minus gamma b squared. So power is conserved, right? Magnitude of gamma b was reflected out of the total, right? So then what must have been transmitted is 1 minus that quantity. All right. So a transmission line analogy is very useful in solving these problems. And I suggest that you always try to form a transmission line model or transmission line analogy with these problems, because it'll make your life much easier. So to greatly simplify the problem, as the vector nature is removed and the problem is formulated in terms of scalar waves. So you don't have to think about vector components and all of that when you make these transmission line analogies. So how do you do it? All right. Well, we have the problem, same problem. We have the incident field here, which is a plane wave, normally incident upon some semi-infinite interface. And we have epsilon 2 mu 2 here, epsilon 1 mu 1 there. We form a transmission line out of this by considering a pair of terminals separated by a distance d to make a two-wire transmission line, right? And the electric field is across these terminals. So we can define a voltage, which could be E incident times D, right? Okay. Now we can define a convenient set of terminals separated by a distance D, and we can define a scalar voltage, E incident magnitude times D, in terms of volts. Good. So on the left-hand side, we have the characteristic impedance of the transmission line is the wave impedance of the intrinsic impedance of the medium. All right? Which is Z01 equal to A to 1. So you have two transmission lines here, one and a junction between the two, right? On the right-hand side, we have this medium, which has characteristic impedance Z02 equal to A to 2. Now you go back to your very first class in fields and waves, and you apply all the formulas you learned there to calculate the reflected and transmitted fields, or the reflected and reflection and transmission coefficients. So here we have, from that class, gamma is equal to Z02 over Z01 divided by Z02 plus Z01, right? It's the exact same formula we derived considering fields and vector nature of the waves and applying boundary conditions even. I mean, that's how you get to these anyway, right? But these you probably memorized when you first learned them. So it's a much more familiar way to solve these. And transmission coefficient 2Z02 over Z02 plus Z01. So you've already seen these equations in your previous classes, all right? Okay, so this is a local model. So everything that's happening is happening here at this point. If it's some kind of medium that's finite, then these edges might contribute, or you might have some coupling between one point on the interface and another. So you might get, this might be an approximate model, whereas it's exact if it's an infinite interface. You can though, but you probably do some kind of numerical method or something, or modal expansion, mode matching and things in that case. All right, that was easy. Let's do oblique incidence, yeah? We have to break this into two different cases. There's a TE polarization case and a TM polarization case. So why do we do that? Because no matter what the polarization is, even if it's oblique. So first off, let's describe the geometry. So we have the interface here. We have an incident field now, which is in this direction. The incident field is traveling in this direction with an angle θ1 with respect to the interface normal. The interface normal is here, points into the incident medium, and it's denoted as n hat. In this case, it's minus z. We call the incident field wave vector beta I as a vector. In this particular case, transverse electric polarization, the electric field is polarized in and out of the board, right? So first off, polarization could be some arbitrary angle, right? Or some arbitrary arrangement where I could have one component of the electric field in and out of the board, and another component of the electric field in the plane of the board, right? If the electric field is like this, then it would have a description in terms of two bases or two components, one in the board, in the plane of the board, and one orthogonal to the plane of the board, right? So we break our electric field into these two cases, and we apply, or we solve for the reflection and transmission coefficients for these two cases separately. We apply those reflection and transmission coefficients to the components separately, and then we reassemble the electric field after for the two cases, all right? All right. This is called TE. What does that mean? Transverse electric, which means we've looked at something like this when we were writing plane waves, right? As a matter of fact, when we were writing plane waves that had some kind of arbitrary polarization, we broke it into TE and TM components, right? So same thing here. So we have the incident field. We call this TE, means transverse electric. The electric field is transverse to the plane of incidence. The plane of incidence is defined as the plane containing the normal vector and the incident field vector. Right? Two vectors span a plane. So to define that plane, the normal to the interface, negative z hat, and the incident field wave vector beta incident. All right. So the electric field is orthogonal to that plane. We call it TE. All right. So we denote the electric field as E perpendicular because the electric field is perpendicular to the plane of incidence. E perpendicular, let's write it out. So we know it's in the y hat direction here, right? Y hat, we give it a name, E incident perpendicular. We write e to the minus j beta incident dotted with r in general. Beta incident here, so beta incident is like this. It has this component and it has that component. This electric field vector here, or this angle here, is this angle, theta incident, right? So beta I times cosine of theta gives you z. Beta I times cosine theta gives you z. And beta I times sine of theta gives you x. You guys should have done this in the last lecture. We went over all this, right? We just call it E naught here. Because later we'll have E parallel, right? So E perpendicular, the amplitude of the perpendicular polarized electric field incident, is nothing but E naught. But next we're going to consider E parallel, and that's going to have two components, right? An X and a Z component. So that will break up differently. All right, the magnetic field's in plane. So you can find the magnetic field. I'm not going to go into detail on how to write these because you guys learned this in the last lecture. All right, but what we have to remember is we divide by eta 1 here. And E reflected has gamma B times E naught. And now we denote it as a perpendicular reflection coefficient. We write H reflected. We have E transmitted. We have transmission coefficient multiplied by E naught. And we ensure that we use beta 2 here. All right. And H transmitted has eta 2 here and a transmission coefficient in the transmission side, or transmission coefficient, and beta 2. All right, now you just apply boundary conditions. And by applying the boundary conditions, E perpendicular incident plus E perpendicular reflected, tangential components at the interface z equal to 0 has to equal to the tangential component of the transmitted electric field perpendicular component. And that's the continuity of tangential E and the continuity of tangential H. If you apply these boundary conditions, then you derive these two expressions, which constitutes two equations. So here's equation 1 and equation 2, and 4 unknowns. What are those 4 unknowns? They are, let's see, they are beta. We don't know the betas, right? So there's beta, gamma, beta, transmission coefficient, beta. Here we have transmission coefficient, beta, beta, reflection coefficient, beta. That's it, right? So betas and beta, beta 2, gamma, perpendicular, and transmission. Transmission coefficient. If you solve those equations, okay, so what you can do first is you can find that theta reflected equals to theta incident from Snell's law of reflection. How do we do that? Well, let's do that. So from the first equation, what do we see? From the first equation, we have, let's see, we have x sine theta. I think you have to solve these together, right? Yep. So you have to solve these. So I'm not going to do it. Do it for your own understanding. Solve these two equations and 4 unknowns. There's a way to rearrange them, right? Let me see here. Yeah, there's a way to rearrange them. Okay, anyhow, you derive the following expressions. You get theta incident equal to theta reflected, Snell's law of reflection, which you expect, and you get beta 1 sine theta I equals to beta 2 sine theta t, which is Snell's law of refraction. So these come from applying boundary conditions at the interface. Okay, good. All right. So the way that you get these is you also can look at continuity of the tangential components of the k vector. That's also continuous, right? So that's one way to look at it. So we have this. This is the incident field k vector. That's the reflected field k vector. And, whoops. The transmitted k vector is this one. All right. Now, that means that this component has to equal to this component, and they have to equal to this component as well, right? They all have to be the same k vector. So from there, you can get theta incident equal to theta reflected, and you can get Snell's law of refraction. And you can derive these two coefficients, gamma reflection coefficient and T for the transmission coefficient in the oblique incidence case. So here's some plots of the reflection coefficient and the transmission coefficient for this case, for the perpendicular polarization or the TE polarization, as the refractive index ratio, the permittivity ratio changes. So here we have epsilon 2 over epsilon 1 is 2.56, and we have epsilon 2 over epsilon 1 is 4 or 9 or 16 or 25 or 81. So we see as the ratio of permittivity epsilon 2 to epsilon 1 becomes much, much greater, there's more and more field reflected, right? Obviously, if these two were the same, the reflection or the ratio would be 1 and the reflection coefficient would go to 0, right? Because the interface is not there anymore if both the media have the same permittivities. And they depend on incidence angle. So as the incidence angle changes, you get more and more reflection, right? And you get less and less transmission here in this case. And you get, so this should be kind of opposite, right? 81 is down here, 81 is up here. Okay, good. So we can make a transmission line analogy to solve this problem, which is even more useful than the normal incidence case. Okay, so we do the same thing. We have some electric field here polarized at some angle. We make a transmission line with its terminals directly across the electric field so we can define a voltage. Once we do that, we can define the wave impedances or the characteristic impedances of the transmission lines. On the left side is now denoted as A to 1 TE because it's polarized. And A to 1 TE is A to 1 over cosine of theta incident. So that's the trick to using the transmission line analogies for these oblique incidence cases. You just have to use the TE polarized characteristic impedances. All right? Z naught 2, A to 2 TE is A to 2 over cosine theta T. For the TM case, or the parallel polarized case, this will be A to 1 times cosine of theta and A to 2 times cosine of theta. And I think we're going to go over that. Okay. So then you apply the exact same formulas as for the normal incidence case. Except now you have these characteristic impedances, this one and this one. So that makes it much easier. If you substitute this and this into here and here, you'll get these expressions. Great. Let's do the parallel polarization case, the transverse magnetic case. So now we have the electric field in the plane of the board. The magnetic field is now in and out of the board. So this is parallel to the plane of incidence. That's why it's denoted as subscript parallel. And we have to resolve this electric field into its X and Z components now. So we do that. We had practice doing this in the last lecture. So we have E parallel incident here is now contains an X and a Z component, and the beta vector is the same as before. Then we have the incident magnetic field we can find using our right-hand rule if you'd like. The reflected electric field We can also write that in terms of its x and z components, and it now has a gamma parallel. We have the magnetic field incident, reflected, and we use gamma now, gamma perpendicular, and we can write the transmitted electric and magnetic fields. Applying the boundary conditions, we get these two expressions. We have two equations and four unknowns again. By equating the real and imaginary parts of these two, this system can be made into four equations with four unknowns. Okay, if you do that, you get these expressions here. So these are now the reflection transmission coefficients for the parallel case. And what we see is a different behavior. Remember before, the reflection coefficient never went to zero. So you can never eliminate, let's go back, you can never eliminate reflections, no matter what angle you come in at, right? Here, there's a special angle where you can eliminate the reflected field, and that's called the Brewster angle. We'll look at that. But the reflection coefficient for this polarization only, this component, goes to zero at various angles for different permittivities. Where, here?
Why does it go up to 1 for the reflection coefficient?
Oh, here. Here?
Yeah.
That, so what happens is if you come in at a grazing angle, then it basically, if you come in very, very shallow, like a grazing angle, then everything's reflected. If you come in at 90 degrees, you're essentially not even really, 90 degrees, you're just parallel to the interface, right?
So what is the intersection to the all English?
No, that's nothing. That's, you mean these points here?
Yeah.
Those are just continuations of, these are all separate cases, different permittivities. So don't think about the intersections. They have no meaning here. Yeah, that's a great question, but that is not the case because what happens here is there is, that's a great point. So when, I think what's happening here, when we get to, let's look at the Brewster angle. When we get to the Brewster angle, I think what's happening there is that it's either going into a surface wave at the interface, which we'll study, but I think that happens at more for the total transmission. No, I think, let's see. Let me jump ahead. So here's the Brewster's angle. Yeah, it becomes a surface wave. Yeah. Okay. So not all of it's transmitted. Some of it gets trapped to the interface. Becomes a surface wave. All right? We'll look at that. Okay, good. So you can use your transmission line analogy here for this polarization. And what you'll have for the characteristic impedance is eta1 times cosine of theta incident or eta2 times cosine of theta transmitted on the other side. Then use the exact same formulas. So these are better. You only have to remember two formulas, which I'm sure you have ingrained into your memory. And you just have to be able to write down the correct characteristic impedances for these polarizations, for these cases. All right? Great. Okay, so you can do this in a multimodal way. You can combine the two polarizations and do it in a matrix form. I'll let you look at this later on your own. I don't use this very much, but it is possible to do it that way. All right, so Brewster's angle. What do we say with Brewster's angle? We said that the reflection coefficient goes to zero. So to find that angle, let's set the reflection coefficient only for the parallel polarization case equal to zero. And we'll solve for the angle theta. All right, if we set this equal to zero, then the numerator has to be zero, so that becomes this equation. And if that's equal to zero, I can throw this term to the other side, and we get this expression here. Now what I can do is divide both sides by eta1, and we get this expression. I can write eta1 and eta2 as, okay, so I square everything, square both sides. And then, all right, okay. So you square both sides. So this is eta2 squared. This is eta1 squared, right? Because eta is the square root of mu over epsilon. And from there, And then cosine squared is 1 minus sine squared. Square both sides, write it like that. Then what you can do is you can, so we've written this now in terms of theta incident. What are we using there? So I think we're using some form of Snell's law, right? Data transmitted. Yes, it's Snell's law of transmission. Snell's law, we apply Snell's law, we get to this left-hand side. And from there, we can solve for sine of theta I and take the inverse sine of both sides. We end up with this expression for non-magnetic media. All right? Okay, good. So what is happening here? We have an incident ray which is unpolarized, for example. So it has some component in and out of the board and some component in the plane of the board. So that's what those dots mean, the component in and out of the board, which is the TE component, and the dots in the plane of the board are the TM component. We're incident at the Brewster angle theta B. If we're incident at the Brewster angle, what's going to happen? Well, the reflection coefficient for this polarization, the parallel component, the ones that are in the plane of the board, this component, right, is going to go to 0. So you'll see the transmitted ray only has TE components. So it's a polarizer. You can use it to design a polarizer. The transmitted ray will have both polarizations still, right? Okay, let's look at this a little further. So what do we have here? So here's a simulation or animation of the Brewster angle, the Brewster effect. So we have an incident pulse, which shows the planar wavefronts, right? That incident pulse is incident at the Brewster angle on some interface. And the reflected field here. Oh, no. Sorry. Yeah, I was about to say, it doesn't look like this doesn't look like Brewster angle. So now we're talking about total internal reflection. So let me look back at your question then, because that's a good question. I have to think about that, and I'll let you know. But in this case, okay, now we're studying total internal reflection, so this makes more sense. So yeah, we have a pulse coming in at some angle, right? This angle has to exceed what's called the critical angle, and if it's incident at an interface where the index of refraction of the outer media is less than that of the inner media, so this permittivity. Oh no. Yeah, this is, okay, so this permittivity here, epsilon here, let's call it 2, epsilon 1, we know that epsilon 2 is less than epsilon 1, all right? If that's the case, then there will be a critical angle, and an incident field will completely reflect, totally reflect, no transmission, right? So there's no field transmitted into the outer media. All right, so how do we find that angle? Well, first we take the reflection coefficient for the perpendicular case, and we set it equal to 1. We want total reflection. All right, if we set that equal to 1, then we can take the magnitude and set the magnitude equal to 1, right? We want total internal reflection in terms of its magnitude. So this is satisfied if the second term in both the numerator and denominator is imaginary. All right, so if these two terms are imaginary, then this equation can be satisfied. And if you do that, and we can end up with this expression, right? First, what we're doing is constructing that expression. Cosine of theta t is equal to the square root of 1 minus sine squared of theta t. That's an identity. All right, we can use Snell's law to write theta t in terms of theta I, or sine of theta t in terms of sine of theta I. All right, we get this expression. Then we can factor out a minus sign, we get this expression, okay? So in order for the above to hold, this total internal reflection, we want the incidence angle to be greater than some critical angle, which is defined like this, inverse sine of the square root of mu2 epsilon 2, or mu1 epsilon 1. And if it's non-magnetic, or if the permeabilities are the same, then we can write it like this. Okay, so this is the definition for the critical angle. So if we're incident at an angle greater than this critical angle, which is defined as the inverse sine of the square root of the ratio of the permittivities, then we'll have total internal reflection. Those are the wavefronts, right? So like the real part of the electric field. So you have sort of oscillating wave, like a sinusoid. So one color is the maxima, another color is the minima. And you can see a surface wave being generated at the, or the evanescent fields at the interface. All right. So this can only hold when epsilon 2 is greater than epsilon 1, as I was saying, for this inverse sign to make sense. So total internal reflection only happens when a wave travels from a more dense medium to a less dense medium. Great. So let's look at this total internal reflection a little bit deeper. Okay, so what's really happening here? All right, let's dig into this. So the animation's still there on the right-hand side. We have three cases here. The first case is when theta I is less than the critical angle. So the critical angle here is denoted with this dashed line, right? Theta C. And theta I here for this incident wave vector is less than the critical angle, right? So this is the critical angle here, and we're incident at this angle here, which is less than this critical angle here, right? All right, in that case, then what's going to happen? We're going to have ordinary reflection and transmission, right? So this is the Snell's law of transmission. Then we have the reflection and transmission coefficients here for this case. And the Snell's law of reflection is here. So all four expressions for this case. This is the ordinary case. We have a transmitted field, a reflected field, and an incident field, right? All right. Now, what happens exactly at the critical angle? If we're incident at the critical angle, then theta incident is equal to theta C, right? Still, we have theta R equal to theta I, Snell's law of reflection on the left-hand side. But now what we see is the transmitted wave has become a surface wave. The beta vector is along the interface now for the transmitted wave. There are constant phase planes are orthogonal to the beta vector. So you can see that it's like a plane wave traveling along the interface. But it's evanescent, it decays in this direction. So the amplitude, it doesn't travel, it doesn't, in this medium, it's evanescent, right? So the amplitude will decay like that. We can see that here, right here, right? Right there is a surface wave. If you watch the animation, it's traveling along the interface. It has wavefronts, black and white ones, right? These black and white wavefronts are traveling in that direction. The beta vector is that way. It's evanescent in this medium. See, it decays exponentially, the amplitude, but it travels in that direction, along the interface, right at this critical angle. Okay. All right. So if you, and then here's all the expressions for the reflection and transmission coefficients, and you can solve for these. So the transmitted angle now is 90 degrees. And we have a reflection coefficient of 1, transmission coefficient of 2, and we have the electric and magnetic field transmitted like that. So wait, I take that back. This transmitted field here is not evanescent. This surface wave here is not evanescent in this medium. It's a plane wave in that medium, bound to the interface. So this animation is for the next case that I'm going to talk about. So if you come in at an angle exceeding the critical angle, you can solve all of the expressions. I've listed them here for you. And what you find is that you end up with this expression, exponential term for the transmitted electric field. E transmitted has an exponential decay in the z direction. So that's when it becomes evanescent. When you exceed the critical angle, it's evanescence in medium 2. And this animation here depicts that case, greater than the critical angle. At the critical angle, you get this very special case where you have a plane wave in this medium. These are constant phase planes with no amplitude decay. Right? This is the transmitted field here. No z dependence. The what?
Get a square root of it. If it is very small, it either very small as a sine squared, it's a small number.
Well, okay, so this expression here has cosine theta transmitted, has a j factored out already. You're assuming that this incident angle is rather large. It doesn't have to be, right? But it's not near zero. It's theta incident greater than the theta critical angle. And this, when you solve for the inverse cosine of this expression, you get a complex angle. That's one of the characteristics of a total internal reflection, surface waves. You get a complex transmission angle. That complex transmission angle manifests itself in terms of these evanescent attenuation factors. This is in the book, yes. Very good question. So yeah, plane wave bound to an interface it's hard. I wouldn't call it plane wave, but it's a surface wave. So that surface wave, if it's bound to an interface, like a 2D interface like this, then it's evanescent in the direction normal to that interface and evanescent normal to the direction on the other side of the interface, right? It's only not evanescent or traveling wave along the interface itself. It's evanescent in the directions orthogonal to the interface. Evanescent means that the wave is not traveling, right? It exponentially decays. But if it's a traveling wave, then it has phase progression, right? Very good. Okay, yeah, you can derive these expressions. They're in the book. I've listed them for you here for these three cases. Okay, great. All right, let's do lossy media now. So we have a normal incident plane wave, incident upon a medium with loss now. So remember before when we dealt with loss, all we had to do was change the wave impedance to complex wave impedance. And we had to introduce the complex wave number as well. So now we have an alpha and a beta, right? These we derived in the last lecture. So now when we write our incident electric field, we have some E naught, and then it decays in the z direction, e to the minus alpha 1 z. Wait a minute. Why is it decaying in the... Oh, this is a wave. Okay. Let me check if that is the way that they have it in the book. I suppose it probably is. But the incident electric field has this exponential factor there. Maybe that exponential factor becomes 0 when alpha is equal to 0. So this is a general expression. All right. So if sigma is equal to 0, rather, if the incident medium is lossless, then sigma is equal to 0 and alpha goes to 0. So then this could be a general way to write it. Okay. Anyhow, and then we have e to the minus j beta 1 z. We have eta 1, which is a real number. The reflected field is gamma b again. We have this in general, e to the alpha 1 z, and eta 1 a real number. We include e to the alpha 1 z here. Transmitted field now, though, has e to the alpha 2, that will be non-zero, has a transmission coefficient, and we use beta 2. And then we have eta 2, which we know needs to be complex, right? Well, if you evaluate it, yeah, but alpha is going to be 0, right? Depending on how, this is a general form of these expressions. So one medium could be lossy, one could be... But the way you generally do it, though, is the transmission medium is lossy, the incident field is lossless. So we use the same expressions for the reflection coefficient, except now we have the complex wave numbers in general. And the transmission coefficient, we have, oh, okay, no. I think what's going on here is both media are lossy, but they have different losses. Or they can have different losses, right? Different sigma. When I look at this now, what it looks like to me is that we have one medium, half space has some sigma 1, and the transmitted half space has a different sigma 2. If that were the case, this is how you would write it, right? They all have alphas. They all have complex wave impedances. So all of these, A to C1 and A to C2 would be complex. There would be an alpha 1 and there would be an alpha 2. And then you can specialize this to the case when one of the media is lossless. Transmission coefficient, same thing. All the formulas are the same, right? Except we have to be careful to incorporate the complex wave impedance and the alpha now. That's it. So use the same expression. Gamma and T take the same form. So now they use the complex wave impedances. And we saw expressions just like this in the last lecture when we were looking at the power density of waves in lossy media. Good. All right. So oblique incidence now, let's mix it up. We have a dielectric and a conductor interface. So here we have dielectric, like free space, for example. And here we have a conductive or a lossy media that we're transmitting into, okay? All right, so let's do this. The incident field is here. The reflected field we know obeys Snell's law of reflection, so theta r is theta I. And we have theta 1 mu 1 on the left side. And here we have epsilon 2 mu 2 and sigma 2. So the transmission medium is now lossy. And if you solve the mathematics here, if you use, so here's Snell's law, and then we know gamma is alpha plus j beta, but alpha 1 is equal to 0, so we just get j beta 1. And we have alpha 2 plus j beta 2, right? And we know we can write cosine theta transmitted on the left side. So what you do is you write cosine, okay, so this is a different expression, right? Cosine theta transmitted is equal to 1 minus sine squared of theta transmitted, but you can write sine squared of theta transmitted in terms of sine squared of theta incident using Snell's law. This is a different expression here, right? Cosine of theta is equal to square root of 1 minus sine of theta. But this is transmitted. We then write transmitted in terms of incident by using this Snell's law expression here, and then we can come up with this expression. We can write that in polar form, call its magnitude S, and call its angle zeta. All right. Then we write the transmitted electric field as some vector form. It might have perpendicular or parallel components, E2. We have e to the minus alpha 2 plus j beta 2. And then we have cosine of theta transmitted, right? Or no, we have sine of theta transmitted x. All right. So it's the same expression, right? So this is x, sine of theta transmitted. And then we have z, cosine of theta transmitted. But we started here with cosine of theta transmitted is equal to the square root of 1 minus sine squared theta transmitted. And then we use this expression to relate theta transmitted, theta incident. And we ended up with this expression, right? Now we have cosine of theta transmitted. We put it here, so it ends up here. We have sine of theta transmitted, which is this expression, or this one rather, and we put it here, right? Okay, good. All right, so now we have e2 e to the minus alpha 2 plus j beta 2, and we can write this in using Euler identity, the exponential we can write as cosine plus j sine. All right. The reason why we do that is we're going to factor out some things here. So we can write this as alpha 2 cosine zeta. FOIL this out, and we get this expression, right? And then we're going to call this, why did we want to do that? Well, we wanted to take all the real exponentials and group them, and all the complex exponentials and group them. So we can have an expression with like e to the minus alpha z multiplied by e to the minus j beta, right? But this is oblique incidence. So now we know what the attenuation is, and we know that the phase delay direction is, right? What the phase delay is, phase term. So what does this show after we do this mathematics, right? Mathematics are straightforward. Come back and take a look at them. What we find is that the amplitude decays in the z direction only, normal to the interface. But the phase delays in the direction, in some oblique direction in terms of x and z, right? So look here, we have constant phase planes are at the transmission angle. So we transmit at some angle, right? Transmit at this angle here. We have beta 2, we call it, but the angle here is zeta 2. Well, and we'll look at that, all right? We transmit at some angle. The phase planes are orthogonal to this k vector, right? But the amplitude planes, these are the constant phase planes, the constant amplitude planes are orthogonal to the z direction. So we have some kind of thing called an inhomogeneous plane wave. The amplitude decays in a different direction than the phase planes are, right?
So the energy is different direction.
Yeah. So the wave is traveling this way. The phase planes are orthogonal to it, but the amplitude is decaying in a different direction, right? Different coordinate dependence. A way to do what now? Yeah, definitely. You can, so this is all because of the loss, right? So if you tune the loss, maybe you can tune the way the power decays in particular directions. Yeah. Very good. Okay, so we wrote this like this. So here's P and here's Q. We call this alpha 2 equivalent. And then Q is the direction of, is the wave number in that direction, right? Okay. So let's look at the constant phase planes. We have E2 e to the minus ZP and then e to the minus J beta 1 x sine theta plus ZQ. All right. Let's look at the phase terms only. And we end up with, okay, so beta 1 x sine theta I plus ZQ. We know what Q is here. We know what, we know what Q is. That means we can write it in this form. All right. After some algebraic manipulation. If you write it in that form, then we can define, so here it is repeated. We can define an angle, a transmission angle, psi 2, such that if we define U as beta 1 sine theta I, so here's beta 1 sine theta I, here it is again here, here it is again here. If you define it like that, then we can write this first term up here. We can write this first term here like this, U over square root of U squared plus Q squared. All right, we can call that sine of psi 2. We're trying to find the angle psi. And we can write the second term as Q over the square root of U squared plus Q squared. And that becomes cosine of psi 2. So think about it like this. We have some angle here, psi 2. And if we define one of these sides as Q and one of them as U, so sine is opposite over hypotenuse, right? So that means the opposite is U, and this is Q. And this is the square root of U squared plus Q squared. So I can define all these trigonometric relationships here. I can define these trigonometric relationships, sine and cosine, in terms, I can convert this argument into a sine and a cosine, right? With this definition. All right. No, it's not hyperbolic. It's regular sine and cosine. Well, okay, yeah, maybe. What it is here, though, is you can define a triangle here, right? Okay, here's the general expression that we derived before. If I make U equal to beta 1 sine theta 1, then I get U into X square root of beta, or U squared plus Q squared, right? So I can say this will become sine of psi 2 into X. This will become cosine psi 2 into Z. And the way I can write this quotient here is define psi 2 in some triangle. I have the opposite side is U, the adjacent side is Q, and then the hypotenuse is U squared plus Q squared by Pythagoras. And I can say that's sine of theta, or sine of psi, opposite over hypotenuse, right? Okay. So psi 2 then is nothing but the inverse tangent of U over Q. That's the transmission angle, psi 2 here. Okay, and then you can write the electric field in terms of this new variable U, and you end up with this expression here, and we have some unit vector in the direction of propagation, n psi, and we do beta times n psi is nothing but sort of a beta dotted with r. E to the minus j beta dotted with r. So we're trying to write it in terms of that form. So the conclusion is that the true angle of refraction is psi 2 and not theta transmitted, because theta transmitted is a complex number. The wave travels along a direction defined by this unit vector n psi, and the constant phase planes are perpendicular to the unit vector n psi. Constant amplitude planes are perpendicular to z. So go through the mathematics. You're going to get a homework problem to do that. So you'll go through and derive all of this stuff for yourself. The mathematics is straightforward. It's there. The conclusions and the observations are what you want to draw from it. But you'll get a chance to dig into all of this. All right? Good. Okay, we can do an example. What time is it? All right. A plane wave of either perpendicular or parallel polarization traveling in air is obliquely incident upon a planar interface of copper. So this is the sigma for copper at a frequency of 10 gigahertz. determine the angle of refraction and reflection coefficients, angle of refraction, and the reflection coefficients for each of the two polarizations. All right? Okay. So let's draw it first. What are we looking at here? We have a plane wave of either polarization is traveling in air obliquely. So we have air in this medium. It's incident obliquely at some angle. A planar interface of copper. So over here we have copper. And the frequency is 10 gigahertz. Determine the angle of refraction and the reflection coefficients for each of the two polarizations. All right. So the first thing we need to do is we need to determine whether what the alpha and the beta are in medium 2. So let's call this medium 1. This is medium 2, right? So first thing we do is we look at this ratio. I don't know if you remember from last lecture, we had that table of alpha and beta, and there were different cases: good conductor, good dielectric, and the exact formulas. So whenever we discerned whether it was a good conductor or good dielectric, we used this ratio, sigma over omega epsilon. So the first thing we're going to do is calculate sigma over omega epsilon. We know epsilon 2 is nothing but, epsilon 2 over here is epsilon naught, and it has a sigma, right? So here's sigma of medium 2, copper. Here's 10 gigahertz, omega, and then we just have epsilon naught here because metal has, at these frequencies, epsilon is equal to epsilon naught. Then we find that ratio to be much, much greater than 1. All right, that means that we can say from that table that alpha 2 is approximately beta 2 is equal to the square root of omega mu sigma over 2. Okay. So now we can use our Snell's law of transmission. We know what alpha 2 and beta 2 are now from here. We plug that in, and we set that equal to 0. Let's see, what are we doing here? So this is equal to that, is equal to this. So why do we set equal to 0? Sine of theta transmitted. Sigma 2 is much greater than 1, so theta transmitted equals to 0. So, okay. I have to go back in and find why. I'm trying to understand why we set equal to 0 here. So there's Snell's law. Plug in this expression here. That's correct. That's correct. Okay. Okay. So theta transmitted then is equal to 0 when sigma 2. Okay, I know what it is. So when sigma 2 is much greater than sigma 1, right? When the conductivity is high, then the transmission angle is basically normally into it, right? Let's see how else I can say that. If the permittivity, okay. It's like when you're obliquely incident on a conductor, no matter what angle you come in, the transmitted field is always normally into it, right? I'm trying to think of the best way to. That's what it's from. It's from here. So we know that the transmission angle is 0, right? Oh, no. Okay, sorry. This is what's going on. This is equal to 0 because sigma 2 is very, very large and it's in the denominator. Okay, so it's approximately 0, right? 10 to the 7. So then the transmission angle is nearly normal into the medium. Okay, we know cosine of theta transmitted is equal to this from the last slide in polar form. The transmission magnitude of that is going to equal to 1, and the transmission as angle psi is going to equal to 0 because of the normal incidence thing. If we go back, we can find that, right? Let's find where S and P is here. So P is here. We have zeta, alpha 2, beta 2. These are both equal now, right? Okay. P and Q, we have alpha. So here's P, here's Q, right? So let's do that first, and then we'll come back to these two because these are functions of P and Q. So P is this, which is approximately alpha 2. Okay, if you write that out, and then here's beta 2 here. And then we can find psi 2 from the expression we derived before, and we end up with this expression here. So, okay, yeah. So here, due to the high conductivity, the transmission angle is 0 degrees independent of the incidence angle because of the high conductivity, and the transmission angle we find has to fall within this, has to be less than this value here, which is, so you know what? Let me go through the details of this problem. I don't want to just throw it at you like this. Let me go through the details instead of trying to work it out right now. What? I think we're going to talk about skin effect here soon. Yeah, what I want to do, I'm gonna go read this. I'm gonna go look at this problem again and see. I think I skipped some steps here, and I did this a while ago, so I want to go back and look at it. And then we'll go over this next lecture. All right. Instead of trying to struggle through it now. All right, good. So we'll come back to this example. Okay. Good. What do we have here? So let's look at the derivation of the input impedance. What is input impedance? So we have the reflection coefficient. So we have the same problem here. We have epsilon 1 mu 1 and epsilon 2 mu 2. We have an infinite planar interface. We're coming in normally incident. The reflection coefficient at the boundary of the single planar interface under normal incidence was found to be this, right? From the first slide, or the first thing that we talked about today. We can also translate this reflection coefficient and reference it at a distance of z equal to minus L. So here it's gamma at the boundary, but we can also reference it back here somewhere and say, what is gamma looking in this direction at this point, right? And the way we do that is we say, well, gamma at z equal to minus L. This gamma b you can consider as z equals to 0, is at z equals to 0, right? Okay. So now it has no superscript b. Gamma at z equal to minus L is nothing but E reflected as a function of z divided by E incident as a function of z. We wrote these expressions down in the first slide we studied today. And evaluated now at z equal to minus L. So we end up with gamma b E naught E to the j beta 1 z here divided by E naught E to the minus j beta 1 z. E to the plus j beta divided by E to the minus j beta, but now we're going to say z is minus L instead of z equal to 0. And if we do that, we end up with gamma b and E to the minus 2j beta 1 L. All right. So what we see here is that by translating the reflection coefficient to some distance here at minus L, so z equals to minus L, we introduce this phase term here, which accounts for shifting the reference plane of where we define the ratio of the field amplitudes from z equal to 0 to z equal to minus L. Yeah? Okay. We call that the gamma in at z equals to minus L. Okay. Good. So now, just to the right of the boundary in medium 2, the input impedance in the z direction is equal to the intrinsic impedance in medium 2. So just inside this medium, we can say z equal to 0 plus the input impedance is equal to the intrinsic impedance of the medium. So if we look in this direction, what impedance do we see? We see nothing but an infinite medium of wave impedance eta 2. Yeah? All right? The input impedance at a distance z equal to minus L can also be found in the medium here, right? So this is the input reflection coefficient, but here we're going to look at input impedance. We take the total electric field divided by the total magnetic field, which is the definition of impedance, and we evaluate at z equal to minus L. E incident plus E reflected over H incident minus H reflected, right? And because these are in opposite directions. we can write out the expression here for that in terms of this new reflection coefficient with the exponential term added to it, this one. And if we do the ratio here, we end up with this expression here. This is the well-known formula for transmission line theory for input impedance, but now we derived it from a plane wave perspective. You should have seen this formula before, but now we've just derived it in terms of plane waves. Okay, very good. So what we'll do here is let's not get into this next thing yet. So, okay, I promised you that I will explain this problem a little bit better. I think I typed it up kind of missing some steps here. So what I want to do is I'm going to go through it to make it a little nicer, and we'll talk about it next lecture. So we'll start here next lecture with this example. What I suggest you do is go through and read some of this before about this lossy incidence case here. It's a complicated case, right? So there's a lot of things going on there, and the derivations involve complex angles and so forth. So go through this and come ready to talk about the solution to this problem. We'll start there next lecture. All right, good. Very nice. Okay, good. See you guys.
I had a question on Z part 4 when we are solving for the electric field about which route do we take, because if we take the curl of H equals epsilon E, then it will be a step forward. Would it be the same as curl of E equals minus partial H?
Here, so which problem is this?
For
Polarizations. Okay, very good.
For the electric field. So if I take this route, it would be.
Well, why are you doing all of that? You know how to write down the form of a RHCP or an LHCP plane wave, right? Normally incident. You just have to, you have two components, they're equal in amplitude, but they're 90 degrees out of phase. You know the direction of propagation, right? So it doesn't have to be oblique like that.
It's linear, isn't it?
Is this the... Oh, sorry. So you're not doing the reflection problem. I see. Yeah, okay. Yeah, so once you have the magnetic field, to find the electric field, you use Faraday's law, like you're saying here. Or, sorry, Ampere's law. Take the curl of this magnetic field, and you don't want to use the time domain form, though, right? You want to use the time harmonic form.
I'm just carrying it straight, and I just convert it to time harmonic like this.
Okay, good. So, yeah, this is how you find the electric field.
But would it be different if I use this route compared to this route? With the way the wave propagates, one would be a time step forward compared to.
I wouldn't think of it in terms of time steps like that. So it's all time harmonic. I guess I don't understand exactly what you mean.
So like when we have the E goes to D and D induces D for H, we have like the square, and the wave propagates by inducing in kind of that cycle.
Okay, you mean
If we take this route over this route, then one would be a differential step back or a differential step forward if we're thinking about time derivatives.
Okay. The thing is, you shouldn't be thinking of time derivatives and things with that. It's a time harmonic problem, which is a plane wave, right? And you just use Faraday's law or Ampere's law in time harmonic form, and because I think you're confusing yourself.
Okay.
Don't go all deep into it like that. Hey.
The homework, can I drop the homework somehow in the main board?
Yeah. Just bring it to my office if you need to. Is that what you're saying?
Yeah, but it will be at night, so
Okay, bring it in the morning.
otherwise I have to find and scan.
Yeah, that's fine. You can bring it in the morning.
So about the exam.
Yeah, well, I'll have those graded and returned to you guys soon.
Okay.
Yeah.
So I did all the first problem with all the separation of variable. Okay. So second.
today, and I was like, maybe I shouldn't show up, maybe I should, because I like, wasn't sure about the timing of the wave. So,
That's right, I normally sent it.